Questions 8 through 10 on the 2021 Grade 12 Euclid Math Contest. 5 distinct integers are to be chosen from the set 1 through 8 and placed in some order in the top row of boxes in the diagram. Each box that is not in the top row then contains the product of the integers in the two boxes connected to it in the row directly above. Determine the number of ways in which the integers can be chosen and placed in the top row so that the integer in the bottom row is 9953280000. Well, let's say that those are A, B, C, D, and E. Well, this will be A times B, this will be B times C. This will be C, D, this will be D, E. This will be A, B squared C. This is going to be B, C squared D, and this box will be C, D squared E. Then combining once again, you're going to get A, B to the power of 3, C to the power of 3D, and this will be B, C to the power of 3, D to the power of 3E, and then finally the last box will be A, B to the power of 4, C to the power of 6, D to the power of 4, and E. So we have to somehow get this number to look like that number. And it will help if we can break this up into its prime factors. So 9953280000. And when you do break it up into its prime factors, it's 2 to the power of 16 times 3 to the power of 5 times 5 to the power of 4. And that has to equal this A, B to the power of 4, C to the power of 6, D to the power of 4, and E. Well, how can we do this? So we can do some trial and error, and it shouldn't take that long because there's a few things that, of course, you can recognize immediately. The first is, of course, our list, if you noticed, was from 1 through 8, right? So we had to choose from the digits 1, 2, 3, 4, 5, 6, 7, 8. Well, the prime factorization doesn't include a 7, so the 7 is kind of useless in our case. And the 5 only appears with an exponent of 4. And therefore, we know for sure that it's got to be either the B or the D, because those are the only ones that have an exponent of 4. So therefore, B is equal to 5 or D is equal to 5. Okay, so that really helps. So I'm going to first concentrate on the B equals to 5, this one right here. So I'm going to put 5 right there. And now we have to do some trial and error to figure out what is going to be the other letters. Okay, so let's see what we get here. Well, I've got the 5 taken care of. So really all it boils down to is just 2 to the power of 16 and 3 to the power of 5 is going to be my A, C to the power of 6, D to the power of 4, and E. Okay, so this is what I have to do. Well, the 3's got to go somewhere, right? We have to get a 3 here. And it's going to have to combine, most likely, with a power of 4. So, for example, let's just start with an example. Let's say A is 3. Okay, I've got 3 to the power of 1. But I got to get 3 to the power of 5. So I need 4 more powers of 3. And that will help if the D has a 3 in it. But they have to be distinct, right? They have to be distinct, so I can't put 3 there, but I could put 6 there, because 6 is 2 times 3, right? So that will give me a 3. So if I do put D, that's going to be 2 to the power of 4 and 3 to the power of 4, since that's basically 6 to the power of 4. So that takes care of my 3 to the power of 5. So now I'm left with C to the power of 6 and E, and this is 2 to the power of 16. So let's simplify this. This basically means that C to the power of 6 times E is 2 to the power of 12, right? So that 3 was already taken care of. C to the power of e times e to the power of 12. Okay, well, I think if my c was a 4, that would be 2 to the power of 2 to the power of 6. That would do it. That would give me 2 to the power of 12. And therefore e must be 1. So there we go. It's really just that kind of trial and error. There isn't actually any mathematical way of doing it. It's just plugging in numbers. Okay, so you just keep doing it like this. One thing I know for sure is that the a and the e, if you notice, those have exponents of 1s, exponent of 1. So they can be interchanged. So for example, I can put a 1 there and the 3 there, while keeping these guys the same, 4, 6, and 5. That would work perfectly. All right, so how many more can I get? Well, let's experiment a little bit more. Let's see. Again, I need some values here to get a 3 to the power of 5. So this is still fixed as 5. And I've already chosen my a to be the 3, and I also chose the e to be the 3. So I want the 3 to be something else. Well, I've got a choice between c and d. If I put 3 as c, it's going to be too big. It'll be 3 to the power of 6, and we only want 3 to the power of 5. So my only choice left is d. So therefore, that means I've got a times c to the power of 6 times 3 to the power of 4 times e is equal to 2 to the power of 16 times 3 to the power of 5. Well, that 3 to the power of 4 has to combine with one more 3. So that's going to come from a 6. So the 6 most likely has to go either in the e position or in the a position. So I'll just put it here for now. So that'll be a c to the power of 6, 3 to the power of 4, 2 to the power of 1, 3 to the power of 1 is 2 to the power of 16, 3 to the power of 5. So there we go. We just took care of the 3's. And then that means AC6 would be 2 to the power of 15. Okay, now we got to figure out what to put for A, what to put for C. If I put for C 2 to the power of 2, then that would be A2 to the power of 2 times 6, which is 2 to the power of 12. So that means A would be 2 to the power of 3, which is 8. So there you go. And in a very similar way, you can interchange the 6. Instead of putting it here, we could have put it here, and it'll be the same result. So 6 goes there, and then the 8 goes there, 4 and 3, and of course this is 5. And that's it. Those are the only ones. So we got 4 ways of doing this when b is equal to 5. And you will see that you will get the same sort of system if you do d equals to 5, which is this one right here. If d equals 5, then you will have the 5 here, and you will be able to do the same sort of thing. It'll just kind of shift over. The d now becomes the b, and the b now becomes the d. So this will be 6. This was 4 and 1. This is 1. This is now 6, 4, and 3. This is now the same, 8. But this is 3, 4, and 6. And the final one, 6, 3, 4, and 8. So in total, there are 8 ways of making that work. Prove that the integer 1 factorial times 2 factorial times 3 factorial ... 398 factorial times 399 factorial times 400 factorial all over 200 factorial is a perfect square. All right, 1 factorial, 2 factorial, and so on, all the way up to 400 factorial all over 200 factorial. Now, I'm just going to write out the first few. This is 1, this is 2 times 1, this is 3 times 2 times 1. The next one will be 4 times 3 times 2 times 1, 5, 4, 3, 2, 1, right? 5 factorial, and then dot, 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 right? And then eventually you get to 400 factorial, which is, of course, the 400 times 399. But they've got this 200 factorial in the denominator. So that means I've got to be careful here. Eventually, I'll get up to 199 factorial, which is, of course, 199 all the way down to 1. And then I've got this 200 factorial, which basically cancels with the denominator, like that. And then it keeps on going. So you'll have 201 factorial, and then 202 factorial, like that, all the way until 400 factorial. So basically, what that means is we have to count how many times each number appears. So 2 will appear here, here, here. It'll appear everywhere except the very first one. So since there are 400 of those factorials, 2 will appear 399 times. But this one vanishes, it disappears. So that means 2 will only appear 398 times. So that's something you just got to be careful of. Very similarly, 3 will appear everywhere except here and here, right? The first 2 factorials. So you'd think, okay, there's 400 factorials. 3 will appear 398 times. But it doesn't appear there because that one vanishes. So the 3 appears 397 times. And so on, right? The 4 appears 396 times. The 5 appears 395 times. And so on. And if you notice, these two numbers are adding up to 400, so we can easily kind of figure out when I extrapolate to 199, what is the exponent going to be? Because the exponent plus the number adds up to 400. Now, what is interesting is that this is gone. So I have to basically ignore it. So I've got to jump over it. And I put a little line there just to kind of denote that that was where the jump occurred. So the next one is going to be 201. But be careful. How many times does a 201 occur? Well, it occurs everywhere after that. So from 201 to 400, which is 200 times. So this is a little different. If you notice, those two numbers do not add up to 400. They add up to 401. So it's a little bit different there. Okay, so then keep going. 202 would appear 199 times, and so on, right? Dot, dot, dot. Eventually, 400 would appear just once. Okay, now, what's our goal? We have to show that this whole thing is a perfect square. Something is a perfect square if its exponent is even. So we can immediately just circle and get rid of all the even ones. All the ones that have an even exponent, well, those are going to be perfect squares. So you can just get rid of all those. So we now have to painfully look at just what's left, and that is the one with the odd exponents. And these are the ones that have the odd exponents. Now, in the corner here, I'm going to put something that's important to help us keep track, and that is, you notice these exponents, in the beginning, they kind of just went down by 1, right? But now that I've circled all the ones that have an even, we now left with the odd exponents. You see that? And they're going down by 2. And that's why I put that Q2 there. Which means Q2 referring to every 2. Every second exponent. So 1, then 3, then 5, like that. So that's why I put that Q2 there. Okay, now what do we do? Well, now we have to combine them. We have to make them even. And we can make them even by breaking up the ones that have an even base. Now we're looking at the bases. You notice those are all even. So we can break them up. So for example, this will all stay the same. But this can be broken up into 2 to the power of 199 times 101 to the power of 199. You see that? And then this can be broken up into 2 to the power of 197 times 102 to the power of 197. And then dot, 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 2 to the power of 5 times 198 to the power of 5. And then 2 to the power of 3, 199 to the power of 3. And then finally 2 to the power of 1 times 200. And we notice here that we can start combining. So for example, this 199 right here combines with that 199 because that 3 and that 201 becomes 204, hence making the exponent even. This 197 would combine with a 197 in here. There will be a 197 in here. It'll be 2 to the power of 7, 197 to the power of 7. So that 197 will combine with that. 7 plus 203 is 210, making it an even exponent. So as you can see, it'll combine like that. And eventually all of them will combine that have an even base. So 199, 197, 101, and all the way down to 101. Okay, but I've got to keep in mind that I've got all these 2's left over. I've got 2 to the power of 199, and then 197, and then so on, dot, 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 all the way to 7, and then plus 5, plus 3, plus 1, right? All those 2's. Don't forget that. And then what I have left over are the ones with the even basis. So 102 to the 197, it'll be 104 to the 193, and then so on, right? Dot, dot, dot. Eventually you get to 198 to the power of 5, and then 200. 198 to the power of 5, and then 200 to the power of 1. So now, as you can see, we've moved into a Q4 situation. The exponents here are going from 1 to 5, and they're going up by 4s this time. This right here, that I'm interested in. When you add up all these guys, it's 2 to the power of 10,000, and 10,000 is an even number, so we know that's a perfect square. Okay, in a very similar way, we move right along. And now we have to break up these very similarly to how we did before. So 2 to the power of 197, and then 51 to the power of 197. 2 to the power of 193 times 52 to the power of 193, and so on. All the way until you get to 2 to the power of 5 times 99 to the power of 5. And then the last one would be 2 to the power of 1, 100 to the power of 1. Now these are all multiplications. So, okay, in a very similar way, you can combine. So for example, this 99 combines with that 99. 301 plus 5 is 306, making an even exponent. And very similarly, you'll count it all the way down until you get to this one. There'll be a 51 here, a 51 to the power of 349. If you remember, those two add up to 400. That's why I was able to get 349 so fast. So all of those go. They basically disappear. We can eliminate them knowing for sure that they are perfect squares. And what's left over will be very similar to before. And then we're going to have these 2's. We're going to have 197 plus 193 all the way down to 5. Well, there's going to be a whole bunch in between, plus dot, 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 and then 5, and I believe plus 1, like that. And then on this side, you'll have 52 to the 193, 54 to the 185, because now we're down to a Q8 situation. Let's put that there, Q8. And then eventually, dot, 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 you'll get to 96 to the 17, 98 to the 9, and then finally we've got 100 to the 1. So as you can see, it is a Q8 situation. Okay, this in here, if we add all that up, you get 2 to the power of 990, and that is 9900. So that is indeed even. So that is definitely a perfect square. So in a very similar way, we got to start breaking up those. 2 to the 193, 26 to the 193, 2 to the 185, 27 to the 185, and so on, right? 2 to the power of 17, and then 48 to the power of 17, 2 to the power of 9, 49 to the power of 9, and finally 2 to the power of 1, and 50 to the power of 1. And now, as before, you combine. So the 49 would combine with the 49 here. 351 plus 9 is 360. That's even. And very similarly, all the ones that have the odd bases will combine. And then the 2's, of course, we've got to calculate that. That's going to be 2, 193, 185, plus dot, 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 all the way down to 17 plus 9 plus 1. And then, of course, you got all these guys. The ones with the even bases, 26 to the 193, and then 28 to the 177. And then all the way down to 48 to the 17, and then 50 to the 1. So we are now actually in a Q16 situation. Up here we were still Q8. Yeah, we were still Q8 there. Okay, so now these guys here, when you do that, that becomes two to the power of 4753, and that's surprising because that's obviously not an even number, but that's okay. We can break it up into 2 to the power of 4752 times 2, and then this one we can sort of get rid of because that's just even. It just means that I've got to stick this lone 2 in there because I can't get rid of that because that's not a perfect square. And just like before, we got to start breaking this up now. 2 to the power of 193, 13 to the power of 193. And then 2 to the power of 177, 14 to the power of 177. And then dot, dot, dot. Eventually you'll get to 2 to the power of 17, 24 to the power of 17, and 2 to the power of 1 times 25. Like that. And then as before, the ones that have an odd base, that will combine. So for example, this 25 combines with that 25. 375 plus 1 is 376. And similarly, all the ones that are odd will combine all the way down to that 13. So now let's combine the 2. Don't forget about the 2 that was right here. And then we're going to have to add 193 plus 177, and then all the way down to dot, 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 17 and 1. And then over on this side, we're going to have remaining 14 to the power of 177, and then you're going to have dot, 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 all the way till 24 to the power of 17. And we are still in a Q16 situation right here. Now, these guys in here, that is, when you add it all up, 2 to the power of 1262. And that's even. So beautiful. We got rid of those. Well, we're getting down to the wire now. We just have to split up these guys. And as you can see, there's only 5 numbers left on that side. So let's break up the other side. That's going to be 2 to the power of 177 times 7 to the power of 177. And then it's going to be 2 to the power of, we are Q32, so dropping down by 32, 145, I believe. And then 8 to the power of 145. Then 2 to the power, dropping down by 32, 113. And then 9 to the power of 113. Then 2 to the power of 81, and then 10 to the power of 81, and 2 to the power of 49, 11 to the power of 49, and the last one is 2 to the power of 17, 12 to the power of 17. And we are now in a Q32 situation. Okay, now we can combine. The 11 combines with this, 309 plus 49, that gives an even number. The 9 combines with this 9, 391 plus 113, and the 7 combines with that. So now we are down to the final few. And then the 2 is going to be 177. There's not that many, so we can just list them. 145, 113, plus 81, plus 49, plus 17. And when you add all those up, that's 2 to the power of 582, which is an even number, so that is taken care of. So what's left? What's left on this side? It looks to me like just an 8 to the power of 145, a 10 to the power of 81, and a 12 to the power of 17. And now this is a Q64 situation. Okay. All right. This is it. The final step. Well, this looks like to me like 2 to the power of 145, 2 to the power of 145, and 2 to the power of 145, right? When you break up that 8 to the power of 145. The 10 can be broken up 2 to the power of 81, 5 to the power of 81, and that 12 is 2, 2, and 3. Exponents are 17, 17, and 17. And this is a big multiplication. And what are we at now? Q64, I think, still? Yeah. Okay, let's do this. So, the combination finally, the 3 combines with that to give an even. Then 395 will combine with that to give an even. 395 plus 81 will give you an even. So all we're left with is just a whole bunch of 2's. 2 to the 145 times 3 plus 81 plus 17 plus 17. And that is 2 to the power of 550, which is an even number. So we have proven all are perfect squares. And therefore the entire expression is a perfect square. Suppose that a is equal to 5 and b is equal to 4. Determine all pairs of integers kl for which k squared plus 3l squared is equal to a squared plus b squared minus ab. K squared plus 3l squared is equal to a squared plus b squared minus ab. Well, they've given us values b squared and a squared, so that's 5 squared plus 4 squared, and then this is 5 times 4. So this is 25 plus 16 minus 20. So that looks to me like 21. So we have to just find integer solutions for this expression. Okay, let's see what we get. K and L. When k is 1, I don't think we'll get anything because that'll be 20, and 20 is not divisible by 3. When k is 2, same problem. But when k is 3, we get 18. And 18 is divisible by 3. We get 3 squared plus 3l squared is 21. So actually it's 3l squared is equal to 21 minus 9. So 3l squared is actually 12. So l squared is 4. So l would be plus or minus 2. So plus or minus 2. And I believe that the same thing would hold true if k was negative 3. You get plus or minus 2. And after you keep going here, once you get up to k equals 4, 5, 6, you'll find that it just isn't any more solutions, any more integer solutions. So this is it. So that means my KL is either 3, positive 2, 3, negative 2, or negative 3, 2, or negative 3, negative 2. So those are the only 4. Prove that for all integers k and l, there is at least one pair of integers a, b, for which k squared plus 3l squared is equal to a squared plus b squared minus ab. So let's start by making a little bit of a table and seeing that table, if we can get any sort of a pattern. Now here we go. We have made a little table with some basic values to see what happens. And after you look at this, it's not extremely obvious, but if you stare at it for long enough, it seems from the table that A is equal to K plus L. and b is equal to k minus L. See, it works out for all of them. If you go through the table, 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, and then 2 minus 1 is 1, 3 minus 1 is 2, and 1 minus 2 is negative 1, and so on. So when you have that table, it kind of helps. So if k and L are integers, and since a is equal to k plus L and b is equal to k minus L, a and b will both be integers. So let's see what happens when we plug it in. So we've got k squared plus 3L squared, and that's got to equal a squared plus b squared minus ab. Okay, so let's see what we get. Let's start with this right side here. So the right side would basically be substituting these values right here for a and b. We would have k plus L squared plus k minus L squared minus k plus L times k minus L. So this is k squared plus 2kl plus L squared plus k squared minus 2kl plus L squared minus k squared plus L squared. And then a whole bunch of stuff cancels, I believe. This cancels with this cancels with that, and all you're left with is k squared plus 3L squared, which is identical to the left side. So left side equals right side. Great. So that means that those integers a and b satisfy the equation. And therefore, for all integers k and L, there is a one pair of integers at least that satisfy the equation. Now let's move our attention to part C. Prove that for all integers a and b, there is at least one pair of integers kl for which k squared plus 3L squared is equal to a squared plus b squared minus ab. Okay, in a very similar way, let's make a little bit of a table and see if we can get any kind of pattern. So you start plugging away values of a and b and see what we get for k and L. So here's a and b, and here's k and L, and we got those with that standard equation. But there doesn't seem to be much of a pattern, but when you group them up into odd and even kind of situations, the patterns become a little bit more easier to identify. So for example, in this, you'll see that all of the values of a are even. So a is even here when you regroup them like that. And then here, you'll see all the values of b are even. And then these ones are where both a and b have been chosen to be odd. And after some careful observation of this, hopefully you can conclude something that isn't necessarily easy, but it is as follows. That for this scenario where a is even, k is a over 2 minus b, and L is just a over 2. And you can verify that from these numbers. From this scenario, when b is even, k will be b over 2 minus a, and L will be just b over 2. And the final scenario where both of them are odd, k will be a plus b over 2, and L will be a minus b over 2. Okay, so now what we have to do is we've got to plug it into the equation to show that it actually works. So let's start with if a is even. If a is even, then we've got to show that this equation holds true, that k squared plus L squared, 3L squared is equal to a squared plus b squared minus ab. Okay, well, let's plug it in. These are our values for k and L. So that's going to be a over 2 minus b squared plus 3a squared over 4. And we're just going to concentrate on the left side here. And that gives me, let's see here, a squared over 4 minus ab plus b squared plus 3a squared over 4. And that is going to be a squared plus b squared minus ab. So that does indeed include, it does indeed equal the right side. So there we go. We proved that one. And we do the same thing if b is even. Now we take our values here and we've got to plug it into that equation. So that means we have b over 2 minus a all squared plus 3b over 2 squared, and therefore that's going to be b squared over 4 minus ab plus a squared plus 3b squared over 4, and therefore that's going to be b squared plus a squared minus ab. There we go. So that equals the right side also. And then finally, if a and b are both odd, then we will use these ones. And let's see what we get here. So we got a plus b over 2 all squared plus 3 times a minus b over 2 all squared. And that one gives me a squared plus 2ab plus b squared all over 4. And this one gives me 3a squared minus 6ab plus 3b squared all over 4. And when you add this all up, it gives me 4a squared over 4. So a squared, 4b squared over 4, so that's b squared, and then minus 4ab over 4, so minus ab. So again, it equals the right side. So there we go. We just proved that one as well. In the diagram, 11 circles of 4 different sizes are drawn. Each circle labeled W has radius 1. Each circle labeled X has radius 2. Circle labeled Y has radius 4, and the circle labeled Z has a radius of R. Each of the circles labeled W or X is tangent to the other 3 circles. The circle labeled Y is tangent to all 10 of the other circles. The circle labeled Z is tangent to 3 other circles. Determine positive integers s and t for which r is equal to s over t. Well, let's start with this question here, and we'll start by trying to connect the centers here. So I'm going to connect all the centers first from Z, and then we'll start systematically doing it from Y, like this here, like that. And because of the nature of this diagram, it's actually symmetric, so we can just deal with 1/2. And if we deal with 1/2, it should be good enough. Okay, so that's approximately, you get the idea. Now let's label the actual distances. Well, this they are saying is r, and this is r. Now the y part, that's 4. So all of these are 4 right here, radii. And then the x's are 2's, so that's 2, 2, 2, and so on. And then the w's are 1's, so this is 1, 1, 1, 1, 1, 1, and I think I missed a 2 in there. 2. There we go. Okay, so this angle in here is something that I think is going to be very important, so I'm going to call that theta because I can see a cosine law situation right there. But in order to get that angle, I'm going to first have to get these angles, right? And then subtract it from 180 because these are all about a single straight line that goes from Z all the way to X. So let's see here. Each of those triangles, it seems to me, all of them have the same sides. If you look at these 4 triangles, right? All of them have the same sides. I'll just draw one, and I think that should be sufficient. And let's just draw one here. You'll notice they all have sides 3, 6, and 5. every single one of them. So if I were to figure out that angle, x, this would be x, this would be x, this would be x, and this would be x. So essentially, that theta would be 180 minus 4x. Okay, I think I can figure out that x pretty quickly with the cosine law. So let's do that. It would be 3 squared is 6 squared plus 5 squared minus 2 times 6 times 5 cos x. So that means that 2 times 6 times 5 is 60. So 60 cos x would be 36 plus 25 minus 9. And that is 52. And then divide through by 60, and that would be cos x. And in lowest terms, that's going to be 13 over 15. Great. Now, I do not want to get an actual value for x, like in degrees. And you can do that in your calculator pretty quickly, right? And when you do, I'll just write it out. I don't need it, but I'll write it for you. It's like 29.9. The reason I don't want it is because in the end, they want me to get an actual fractional number for r. And if I start using angles, I'm going to get some decimal. I'm going to get whatever the number is, but it won't be in a fractional format. It'll be some decimal. And I don't think I'll be able to figure out what the fraction is just by looking at the decimal. So I'm going to just stick with this right here. Okay, so here we go. Now eventually, of course, I'm going to have to use that cosine law. So let me just write it out first. That cosine law would be r, be careful here, it's r plus 2 squared is equal to r plus 4 squared plus 6 squared minus 2 times r plus 4 times 6 times cos theta. Okay, great. But here's the thing. That cos theta, I have to get in some sort of a fraction. It'd be a piece of cake to get it in a decimal. X is 29.9 or whatever it is. And I just substitute that in here. I would get, actually I can even do it really quick. If I do that, theta would be 60.29 probably. And then there you go. Put that right there and solve for r. Piece of cake. But the problem is that they've made the question difficult for us because they want it in an actual fraction. They don't want a decimal. Okay, so that means I've got to bring in some trigonometry here. Okay, so trigonometry means I've got to figure out what is the cos of theta. Okay, so let's see here. I think we're done with the diagram. Cos of theta. How do I figure that out? Well, theta is 180 minus 4x. And then we have to now bring in some identities. You guys remember the identities, right? So this one would be cos of 180 cos of 4x plus sine of 180 sine of 4x. Well, the good news is sine of 180 is 0, so this whole thing vanishes. And cos of 180 is negative 1, so this actually becomes negative cos of 4x. Okay, we're down to that. Well, it's still not done because cos of 4x, we have to use the double angle identity, right? So the double angle identity is 2 cos 2x all squared minus 1. Okay, well, we're still not done because I actually don't know what cos 2x is. I just know the only thing I know is cos of x. So I've got to get it in that cos of x form. Let's just multiply through by that negative 1 first. Well, that'd be 1 minus 2 cos of 2x squared. Okay, so now this cos of 2x, again, I've got to use that double angle identity. So that's going to be 2 cos x minus 1. 2 cos squared x minus 1, all squared. Okay, now finally I can put in my 13 over 15. So that's going to be, let's see here, 2 times 13 over 15 squared minus 1. Okay, so we're getting somewhere now. Just don't make any algebraic mistakes here. So that's going to be, let's see here, 169 over 225 minus 1. So this is going to be, what's that, 169 to 338 over 225. And then this minus 1, let's just get a common denominator, 225 like that. And this is going to be 1 minus 2 times 338 minus 1. That's 113 over 225. And that's all squared. And this is going to be, I think I'm going to need a common denominator once again. It's going to be 225 squared, actually. 225 squared. And this is minus 2 times 113 squared, like this. Boy, oh boy. All right, so now let's see, there's going to be some huge numbers here. 50625. 2 times 113 squared, 25538. And then 225 squared, I'll just leave it as 225 squared. Okay, and finally, this is 25087 over 225 squared. And that, what was it? Ooh, that is the cos of theta. Wow. Okay, that is the cos of theta, this big number. Okay, so now finally they made it challenging for us. Now we can go back and use this formula. So let me first do all the expansion stuff. That's r squared plus 4r plus 4, and this is r squared plus 8r plus 16. That's 36. This is going to be minus 12r plus 4 cos theta. Okay, let's put everything on one side. This disappears. The r's 8r minus 4r. And then 16 plus 36 minus 448. Okay, so far so good. And then at this point, I think I have to start expanding here. So this is going to be minus 12 times r plus 4 over cos theta. And let's go back and put in our cos theta value. What was cos theta again? 25087 over 225 squared. Okay. So it was 25087 over 225 squared. Okay. All right. So we are moving right along. So let's multiply through by 225 squared because that's a terrible denominator. So if I do, this is going to be 225 squared times 4r plus 225 squared times 48. And then now I can do this multiplication. It will be minus 12 times 25087. And that is 301044. And then there's an r. And then the next one is 12 times 4 times 25087. And that is minus 1204,176. Okay. Still got some big numbers here. That 225 squared times 4, that is gonna become 202,500r, and then let's just put all the like terms in one spot. That's r, and then this guy here, that is going to be plus 2430000, and then minus 1204,176. Okay, we are moving to the final step here. So that would be 98,544r is equal to 1225824, and therefore r is 1225824 over 98544, and I think that's the answer. R is s over t, so this is my s over t. So s is equal to 1225824, and my t is equal to 98544. Now again, they don't explicitly state that it has to be in lowest terms. Determine positive integers s and t for which r is equal to s over t. But I think you can make this into lowest terms. I think if you divide top and bottom by 48, so divide by 48, it would bring you to lowest terms 25538 and 2053. And that would be in lowest terms, and therefore s is 25538 and t is 2053. And that is the solution for this challenging question, simply because they had us place it in the form of a fraction. Suppose that c is a positive integer. Define f at c to be the number of pairs ab of positive integers with c less than a less than b, for which 2 circles of radius a, 2 circles of radius b, and 1 circle of radius c can be drawn so that each circle of radius a is tangent to both circles of radius b and to the circle of radius c, and each circle of radius b is tangent to both circles of radius a and to the circle of radius c, as shown. Determine all positive integers c for which f at c is even. Well, let's connect the dots here. And when we do, essentially what we're doing is joining centers. They made the diagram in such a way so that those are already identified as centers for us. Okay, great. Now I will label some of these. This is going to be A, and A. This is B, B, and B. Those are the radii. A, B, B, B. And finally, the little guys, C, 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 and C. They already have another C in there. Okay, so now when you look at these triangles, in particular these ones, that one and this one, and the next two, this one and this one, those 4 triangles, you will notice that they have all the same sides. One side is equal to a plus b, another side is equal to a plus c, and the other side is equal to b plus c for all 4. A plus b, b plus c, and a plus c. So that means all 4 of those are congruent. So that means that these angles, these internal angles, this angle, that angle, this angle, and that angle, all of those angles are the same. So if each angle is theta, 4 theta would basically be equivalent to all the way around, which is 360. So each of those thetas is 90. So basically that's a right triangle. It's a right triangle. And because it is, we can use Pythagoras. So let's just use it on this one right here. This is the right angle right there. So that's going to be a plus c squared plus b plus c squared is equal to a plus b squared. Like that. All right. So let's expand this. And when we do, we get a squared plus 2ac plus c squared plus b squared plus 2bc plus c squared is equal to a squared plus 2ab plus b squared. A lot cancels here. The a squareds cancel, the b squareds cancel, and I believe we are left with the following. Just that 2ac plus 2bc plus 2c squared is equal to 2ab. The 2's cancel, and we're just left with ac plus bc plus c squared is equal to ab. And then what you can do is a little bit of fancy algebra, nothing super fancy, but you can first isolate for c squared. And when you do, you get c squared is equal to ab minus ac minus bc, like that. And then you can put in a little bit of fanciness where you put a c squared here and then put a c squared here. And that allows you to factor. It allows you to factor the other side. So this just becomes 2c squared, but this you can factor now, b minus c, and from here you can also factor a minus c, and it gives you b minus c. So therefore this is a minus c times b minus c, and that's 2c squared. So this equation basically is now what it boils down to. With c fixed, f at c is equivalent to counting the number of pairs ab, with c less than a less than b, the condition, and this equation that we have arrived at. So really what it boils down to is trying to find the number of divisors of this little guy, because that is basically what this is. It's two numbers multiplied by each other. So we must find the number of divisors of 2c squared, and that's basically the equivalent of f at c. Well, here we go. You guys know how to find divisors, right? You have to break it up into its prime factors. So for example, if you had 3 to the power of 2, 7 to the power of 1, and 11 to the power of 4, and I said find the number of divisors, it would be take that exponent, add 1, 2 plus 1, take that exponent, add 1, 1 plus 1, and then take that exponent and add 1, 4 plus 1, and you'd multiply these numbers together. That's how many divisors they have of that number. So in a very similar way, if you want to find the number of divisors of 2c squared, we have to first break it up into its prime factors. Now, I don't know what c is, so we have to start giving it some sort of a prime factorization. So let's say c is some prime factors, right? So the first prime factor is 2, so 2 to the power of a. Then after that, some other numbers. 2 to the power of a, because they eventually want f at c to be even. So that makes me think that c has to have a factor of 2, and therefore we'll be able to get an even number of divisors for 2c squared. And then we got a whole bunch of primes, right? I have no idea what they are. So prime to the b1 and prime 2 to the b2, and then dot 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 eventually, like that, to the last prime to some exponent. Okay, so 2c squared therefore would be this is going to be 2a, and then this is 1, so 2 to the 2a plus 1, and then these are all going to be p1 to 2b1, p2 2b2, and so on, all the way to pk 2bk, like that. Okay, so use this sort of style to figure out f at c. F at c basically is the number of divisors of 2c squared. So that's going to be 2a plus 1 plus 1, and then 2b plus 1, and then 2b2 plus 1, and so on, dot dot dot, all the way until 2bk plus 1. Now, we want this to be even. This represents the number of divisors of 2c squared. And we want it to be even. That's what the question is saying, right? Determine all positive integers c for which f at c is even. So we want f at c to be even. Well, you'll notice from here that that is 2a plus 2. And then we have a whole bunch of others. But all those others are odd numbers. You'll notice they're in that form. Dot, dot, dot. They're in the form of odd numbers. So this is the only meaningful part of that equation. So this is always going to be even. 2a plus 1. Because that's what it factors into. Now, the problem is, though, if we leave it at that, we won't be given any valuable information about the nature of A. So what I propose is that you say that this 2A plus 2 is actually a multiple of 4. If you do that, you'll get an understanding of what A can be, because currently it looks like A can be anything. As long as you have this 2 out front, f at C is even. But if A is anything, then C looks like it has no real way of being given any specific condition. And we want a specific condition, so I'll let 2A plus 2 equal 4K. Maybe it's a multiple of 4. So that's even, right? So that means 2A is equal to 4K minus 2. And therefore A is equal to 2K minus 1. And that is a good condition. So that means that the positive integers C, for which f at C is even, are those where C is equal to this format and A is equal to this format. So I'll write that out. Just to conclude, the positive integers C for which f at C is even are those where C is equal to 2 to the power of A, P to the power of B1, ... until P, K to the power of BK, and A is of the form 2K minus 1, meaning A is odd.